Hello, and welcome to this third video on approximation theory. In the previous video, we introduced the L1 and L2 norms, and in this video, we'll generalize this idea to the LP norm. To recap, we're operating in this space we call a normed linear space. This is a vector space, along with something called a norm, which essentially measures the length of a vector. A norm must satisfy four properties. Namely, it must be greater than or equal to 0. If the norm of x is equal to 0, then the vector itself is the 0 vector. If we multiply a vector by a constant, lambda, and then take the norm of that, then that's equal to the absolute value of lambda multiplied by the norm of the original vector. Number 4. The triangle inequality must hold for any three vectors in the space. So if we have three vectors, x, y, and z, then the norm of x minus z is less than or equal to the norm of x minus y plus the norm of y minus z. The LP norm of a vector x, written as two sets of vertical parallel lines with a subscript p, is defined as the sum over the components of x of the pth power of the absolute value of the components, and then taking the pth root of that sum. We also must have that p is greater than 0. So for example, the L1 norm is a sum of the absolute value of the components of x, which in two dimensions gives the absolute value of x1 plus the absolute value of x2. And for the L2 norm in two dimensions, we have the square root of x1 squared plus x2 squared. Think of this as like using Pythagoras' theorem to find the length of the vector x, or even the square root of the dot product of the vector x with itself. A special example, called the L infinity norm, is the absolute value of the largest component of the vector, written as the max over all components of the absolute value of the components. So for example, here we have a two-dimensional vector x with two components, x1 and x2. Since x1 is greater than x2, the L infinity norm is simply the absolute value of x1. So let's try and get a feel for the different LP norms. We can visualize a set of vectors such that the LP norm of each vector is equal to 1. We'll stick with two dimensions, and we can do this for any value of p. Let's start with the L1 norm of x equal to 1. Remember, this is the sum of the absolute value of the components of x. We can already see four vectors which satisfy this equation. These are the vectors pointing to the coordinates 0, 1, 1, 0, 0, minus 1, and minus 1, 0. To find the rest of the vectors with an L1 norm of 1, we can go along one axis an amount, let's say going up the y-axis by 0.9, then we recognize that there's still 0.1 to account for. Because the components just add up, we can simply move along the x-axis by 0.1. And this will give us another vector with an L1 norm of 1. Carrying on with a couple more examples, if we have a y-coordinate of 0.5, then an x-coordinate of 0.5 will give us another vector with an L1 norm of 1. A vector with a y-coordinate of 0.25 with an x-coordinate of 0.75 will also give us a vector with an L1 norm of 1. By now you might have noticed that the set of vectors in two dimensions with an L1 norm of 1 forms a square such that the four corners of the square lie on the points 0, 1, 1, 0, 0, minus 1, and minus 1, 0. Let's move on now to look at the set of two-dimensional vectors with an L2 norm equal to 1. This is equivalent to the solution of the equation x squared plus y squared equals 1. And this describes a circle of radius 1. Notice how the vectors with an L1 norm of 1 are contained within this circle. This is a common property of the LP norm. Taking a set of vectors with an LP norm less than or equal to a given value contains the set of vectors satisfying the same but with LP norms of smaller p. For a p greater than 2, the set of vectors with an LP norm equal to 1 becomes more and more like a square. And then as we approach the limit of p tending to infinity, we end up with this square with the corners at 1, 1, 1 minus 1, minus 1 minus 1, and minus 1, 1. This is why it makes sense to define the L infinity norm as we did as the maximum value among the components of our vector. Any vector in this set has either an x component or a y component, or both at the corners, with an absolute value of 1. And so all we need to define the L infinity norm is to take the length of the maximum component. So in general, the vector satisfying the equation LP norm equals 1 for p ranging from 1 to infinity follows this continuous change from a tilted square to a circle to a squircle to a square, all the time increasing in size. Okay, let's finish off with looking at the LP norm applied to continuous functions. There are many instances in maths where we want to approximate one function with another function. We have Fourier series, Taylor series, interpolation, etc., etc. And so it's important to establish a measure of how close one function is to another, so we know how good of an approximation we have. So just imagine going forward that our goal is to approximate one function f of x with another function g of x. The LP norm for f of x minus g of x on the interval from a to b is written in the same way as we wrote the LP norm for vectors and can be thought of as a measure of the closeness of f and g, or the distance between f and g, if you'd like to stick with the idea of a metric space of functions. And it's defined by this integral. We take the absolute value of f minus g, raise this to the pth power and integrate from a to b. We then take the pth root at the end. To get some intuition as to what's going on, we'll first look at the L1 norm of f minus g. This is the integral of the absolute value of f of x minus g of x between a and b. Showing f of x and g of x on this graph, the L1 norm is the area enclosed between the two curves, and I've shown this in grey. So you can see why this makes a good measure of how close the function g is to f. Ideally, a good approximation would stay close to f of x all the way along the interval, and the shaded area would be as small as possible. The L2 norm of f minus g is a little bit harder to visualize. In this case, we integrate the square difference between f and g, and then take the square root. This is equivalent to going along the interval and at each point drawing a square with sides spanning the difference between f and g. Summing the areas of all the squares, you end up with a 3D volume which dips closer to the xy plane where f and g are closer together. The L2 norm is the square root of this volume. It's hard to get a visual representation for what an LP norm for continuous functions looks like when p is greater than 2. But I want to finish with the L infinity norm for functions. It's pretty simple and very similar to the L infinity norm for vectors. The L infinity norm of f minus g, where f and g are continuous functions on the interval a to b, is defined as the maximum of the absolute value of f of x minus g of x along the interval. Or to put it simply, it's the largest difference between f of x and g of x.